Good morning, everyone, and welcome. Thank you for joining us today for this online webinar titled Beyond the Boiler. My name is Anaïs Gandelin, and I am the communication manager at R2M Solution, and also we are leading the work package 8 for SEEDS. And I am thrilled to be hosting this session today as part of the official EU Sustainable Energy Days. So before we dive in, just a quick housekeeping note. We want this session to be as interactive as possible, so please feel free to use the chat or the Q&A on your right. You can see it on your screen at any time to ask questions, and we have a reserved 15 minutes at the end of the webinar specifically to answer them. Okay. So why are we here today? For a long time, buildings have been treated merely as passive energy consumers, but today the narrative is changing. And with the right combination of renewable energy, electrified heating and cooling, energy storage, and smart monitoring, buildings can become efficient, flexible, and resilient assets within the wider energy system. So this is exactly what we are working on in this project. Our goal is to provide practical, cost-effective solutions for building decarbonization. And today we want to move beyond theoretical concepts and policy jargon and show you real-world applications. To do that, we have gathered a panel of experts who will share exclusive insights from our pilot site. So first, Vula will set the scene by presenting our Greek pilot, which involves the comprehensive decarbonization of a university dormitory. Then Apostolos will give us an engineering focus on the practical integration of heat pumps on the ground. And after that, we have Yakovos will explain the crucial role of IoT, data, and smart automation to make these systems work together. And finally, Bernard will take us beyond the building itself using insight from our Slovenian pilot to talk about energy flexibility and grid stability. So let's get started. Vula, the floor is yours.
Thank you very much. Thank you for organizing this webinar, this workshop. My name is Vula Dimitriadou. I'm a civil engineer working in European funded projects regarding sustainability and the energy transition for more than 10 years. Currently, I'm the Senior Innovation Project Manager in Renel, which is a partner in SEEDS and one of the Greek partners involved in the implementation of SEEDS in the Greek pilot site. Let me share my screen quickly. So today we are discussing the Greek pilot case, smart electrification in action, turning an oil-heated dormitory into a flexible, renewable, ready living lab. So our starting point before SEEDS, you can see the university campus with more than 6 buildings, dormitory buildings, the amphitheater and the cafeteria of the campus, restaurant of the campus. We are using for SEEDS purposes the building in the red circle eclipse, building C1, a student dormitory built in 1997 with 68 rooms. The situation before SEEDS was the heating system was central oil boilers, solar biomass support with the solar biomass support, no cooling system. We were using radiators and domestic hot water storage in the rooms. with nearby sources from a solar field, thermal field, and a geothermal field. In the second picture, you can see where on the left, in the yellow rectangular, is the solar thermal field, and in the smaller yellow rectangular is the geothermal field. And you can see where the building is situated in regards to these fields. So the ambition was to go beyond the boiler and from an oil-based heating system to electrify the heating and cooling system of the university, and also ultimately turn it into a smart, flexible, renewable energy source powered operation. So the goal was not just to get rid of the boiler, but also to create an integrated local energy ecosystem. So what we did, what we really did in the building was to install a photovoltaic system with a reflector, a heat pump, also lots of sensors that could provide us with data for temperature, humidity, and carbon dioxide emissions within the rooms. So we can measure also the living conditions and the air quality of the rooms. We also installed an electric vehicle charging station just outside the building, and all that was connected to each other and with a smart management system that could can indeed control the energy produced and how it's used within the building. The way our system, the pilot side, works is that, of course, let's say the hero here is the heat pump, for which Apostolos will tell us more next. The heat pump uses as an input the geothermal field, the photovoltaics, the energy produced by the photovoltaics, and also whenever it's needed, whenever it's not needed, whatever energy we have stored, we either give it to the electric vehicle charging station, or we keep it stored in the batteries installed within the photovoltaics system. So the energy for the building comes from directly from the photovoltaics system, or mainly from the heat pump. Next, the Greek partners here involved. The Greek partners here involved are the Demokritos University of Thrace, which is the pilot leader for the pilot site. They have provided us with a geothermal field and the building, of course, in which we test all the assumptions we've made for the energy give and take. Renel, who was still is responsible for the electrification project coordination and for installing a bifacial PV system with a smart reflector. Psychtotherm, who is responsible of the multi-source heat pump, and Serth, who is responsible for the digital systems, AI tools, and smart building controls. What Renel contributed to this, practically contributed to this project, was the installation of as you can see in the photo, what we have already installed, the bifacial PV panels and the reflector, which contributes to the production of energy of the PV panels installed, the bifacial PV panels installed. That's it from my side. If there are questions, I think we are going to discuss them in the end. Am I right, Anaïs?
Yes, we have like 15 minutes at the end to discuss.
Okay, thank you very much.
You can still write on the chat or Q&A, and we will answer after that. Thank you, Vola.
Thank you.
Apostolos, the floor is yours.
Thank you. Give me a sec to share my screen. Perfect. You can see it, right?
Yes. Now yes, perfect.
Okay. Good morning to everyone. From our side, I will present the SITS demonstration in Greece, where we developed and installed the multi-source heat pump, where the refrigerant, the natural refrigerant ammonia was employed. The whole system was developed, as Vula explained, for university students' dormitories. And of course, the main idea is to move beyond fossil fuels, fossil fuel boilers, combining electrification, RES technologies as heat sources, thermal storage, and of course, all this into one integrated system, providing both heating and cooling. My name is Apostolos Goudas, and I am a mechanical engineer with a PhD in energy systems design. So all this concept is what we mainly do in Psychotherm. The specific project SEEDS focuses on cost-effective and I would say replicable renewable-based electrified heating and cooling systems. And in this case, it is applied on a building. So the novelty in this lies in combining the different heat sources, solar, geothermal, ambient air, and the integration of all these systems into one completed system, heat pump system. Also the use of ammonia as a refrigerant for this specific heat capacity. The control strategy for sure, and the combination with thermal energy storage. So the whole project is not about heat production, but also improving flexibility with heat storage, renewable utilization, and in general long-term decarbonization potential. So beginning with the need that the solution was necessary, the main concept is that buildings remain one of the largest energy consuming sectors in Europe, account for about 40% of EU energy consumption. And space heating is still heavily dependent on fossil fuels. So decarbonizing building heating is one of the major challenges of energy transition. This kind of buildings in general are relied on fossil fuel boilers that burn either gas or oil. While in the other hand, heat pumps do not create heat from combustion, but so they have no direct CO2 emissions, but they upgrade heat from renewable or ambient sources as described, ambient air, solar, geothermal in this case, and then convert this heat that they upgrade into useful heating or cooling. So this is why heat pumps are such a central technology for decarbonization. They can deliver multiple units of useful heat for every unit of electricity consumed. And this is described with the coefficient of performance, which may reach up to 5, depending on the operating conditions and the heat source temperatures. And of course, it is always compatible with renewable electricity. So in SEEDS, we wanted to go one step further, not just replace a boiler with a standard heat pump, but design a system that, an integrated system that makes better use of the locally available, let's say, renewable sources. Vula presented these sources so you have an idea, and of course adapt them into the operation of the whole building. So here, the slide shows the overall operating concept of the SEED system. At the center is the multi-source ammonia heat pump, which is connected to 3 renewable heat sources. Each source contributes differently. For example, solar thermal can provide renewable heat during sunny periods. Geothermal boreholes offer an almost constant temperature throughout the year. Ambient air acts as an additional source, particularly in mild conditions, when it presents better performance than the other heat sources. And after the multi-source heat pump, the thermal energy storage plays an important role because it helps decouple supply and demand and to make the system operation smoother. So on the demand side, the heat pump is connected to this TES system. And then this TES storage system is connected to the student residential building, delivering either heating during summer, during winter, or cooling during summer. So the key idea is that the heat pump is not forced to rely on a single source, which could operate in reduced performance, but the control logic evaluates the available heat sources, it monitors the conditions, let's say the outdoor air temperature, the ground temperature, the solar collector output temperature, the state of charge of thermal energy storage, and selects the most suitable heat source, either solar, geothermal, or air, or a combination of these sources into one hybrid operation with main criterion the maximum COP. So the heat pump is the heart of the system, but the system intelligence lies in how these heat sources are combined and managed, let's say. So now, why multi-source? That is the main innovation of the system. Why multi-source is better than a single source system? The single source system depends, of course, on only one source and therefore inherits its limitations. Air sources are simple and cost-effective. because they have only one dry cooler. But when the temperatures, the air temperatures gets lower during winter, for example, the performance of the heat pump will drop. On the other hand, ground source systems are more stable because they have the temperature of the ground, which is more or less stable, but they require drilling and higher capex. So the idea here was that we need to avoid this trade-off by combining the different heat sources, solar, geothermal, ambient air, and the control logic can select the most suitable source or even combine them, as I've said. So the heat pump will present the best operation, the best performance, presenting the highest possible COP, so the best OPEX in order to have long-term savings. So this approach, the multi-source approach, improves seasonal efficiency performance, while we can use also renewable energy. We increase flexibility because of the use of TES. And for sure, this system presents a better performance compared to a single source alone. The system, so after the architecture, a few words about the performance of the system. The system is designed for 120 kilowatt for heating capacity and more or less 100 cooling capacity. Heating supply temperature is more or less 45, but of course we can vary the set point. The refrigerant is ammonia, and we have an operating temperature range from minus 10 to 45 degrees outdoor air temperatures. So the value of the system is not only the nominal capacity, either heating or cooling, but the fact that it combines this capacity with RES integration, improved seasonal efficiency and operational flexibility. So we have reduced CO2 emissions, lower operating costs, heating and cooling from one system, which is not really we cannot meet it really often. So greater flexibility and reliability in general. A few words about the ammonia. Why did we choose this refrigerant? Because we want strong long-term environmental profile. Ammonia is a natural refrigerant, so zero GWP, global warming potential, zero ODP. All these metrics are according to F-gas regulation. So the typical refrigerants used for refrigeration and heating lose their power. So also ammonia has a good high temperature capability because it is a well-established industrial refrigerant. And it is a future-proof refrigerant because, as I've said, the regulation gets stricter and continues phasing down high GWP refrigerants. There are a few limitations and, let's say, disadvantages because it is toxic, so safety cannot be neglected. But in the capacity used, firstly, we have installed it outdoor, and the capacity of the unit is limited, so we have so the safety issues are minimum. But of course, we have a proper machine room layout, we have ventilation, gas detection, and in general, everything is compliant with EN 378 standard. So, in general, the refrigerant selected supports the vision of the project, combining zero GWP, high performance, and robustness. Here we have the main components of the system. It's typical ammonia vapor compression cycle. The whole system was designed and engineered by Psychtotherm, and you can see that it is a fully engineered building energy system where refrigeration design, hydraulics, storage, thermal storage, and controls all work together to have an operational system. And finally, up to this point, we have discussed the concept and the design. Here you can see the actual installed multi-source heat pump unit. You can see the green pipes that bring the hot water from solar collectors and geothermal boreholes, and behind the unit, the dry cooler that extracts heat from ambient air. So it has been manufactured and installed as a real prototype system, solving a real world problem as students required both heating and cooling. And here we have an integrated system that provides both based on the operational mode. And what I would like to emphasize here is the transition from design to implementation, having the assembly, the integration of the ammonia refrigeration circuit, the connection to the renewable heat sources, so the hydraulic integration, and finally test the control strategy in the field to fine-tune the operation of the different heat sources and their combination, which is the main challenge. And to conclude, just a few words. The SEEDS project demonstrates a practical pathway beyond the boiler, the fossil fuel boiler, by combining solar thermal, geothermal energy, ambient air, thermal storage, and ammonia as a natural refrigerant. One key also benefit is the flexibility. Instead of relying on one source only, the system can select the most switchable source or combine them, improving renewable energy use and reliability and flexibility. The next step now is to validate, to have a long-term period of operation to monitor the whole system. And finally, a comment about the scale-up challenges have to do with the safety issues about the refrigerant charge, and the controls and hydraulic integration. But I would say that in total, the multi-source ammonia heat pump is a promising pathway for decarbonizing large buildings beyond the boiler. So that's all from my side.
Thank you, Apostolos. Iakovos, it's your turn.
Yes. Hi. Hello. Greetings from sunny Greece, specifically Thessaloniki. Let me share my screen now. This is the presentation. Hope you can see it, right? No?
Yes.
Let me put it in. Now it's better, I hope.
Yeah,
right?
perfect. Yeah.
Okay. So, just a few introductory words about CERT. CERT is a partner in SEEDS in this project, Horizon Europe project. CERT is a large RTO, research and technology organization in Greece. It's the first in Greece in terms of funding and projects. It has It was founded in 2000, and now it has more than 1,600, let's say, people working and researchers, and has 5 different institutes. 2 of them, ITI, Information Technologies Institute, and CPRI, Chemical Process and Energy Institute, are contributing together in this project for the Greek pilot. CERT innovations in general, just a high-level overview, let's say. CERT mostly works with the digitalization part of the pilot. So it develops, let's say, tools, forecasting tools, artificial intelligence tools, and data consolidation tools for the Greek pilot. In specific, we are going to get into more details on that. So the first, the heart, let's say, of our, let's say, developments and works is a cloud data management platform, which is based on open initiatives, open source initiatives like Fireware, in order to consolidate heterogeneous data measured by different IoT sensors, room sensors for internal air quality, for energy, for thermal energy consumption, for the EV chargers, the consumption of the EV chargers, the data from the multi-source heat pump that Apostolos presented, also data from the inverter of the bifacial PV that Vula presented as well, and also weather data, of course, consolidating them into a harmonized and interoperable cloud environment. The second tool that CERT is delivering for this project and for this pilot is an intelligent control service that determines how the multi-source heat pump should exploit available heat sources. So it's a modulation, let's say, tool for selecting the optimal mixture of heat sources each time for the multi-source heat pump provided by Psychtotherm in order to maximize the COP, of course. The third tool is a smart PV reflector control. Is an AI-based, again, control mechanism that dynamically adjusts the reflector angle of the bifacial PV system to maximize the overall solar energy yield on top of traditional, let's say, compared and on top of traditional solar tracking georeferenced approaches. The fourth tool is a predictive maintenance AI tools for heat pump and PV systems. So this is a fully data-driven, again, tool, an intelligent, low-intrusive, in that sense, predictive maintenance service that analyzes operational data to detect early signs of faults and degradation in heat pumps and PV systems. The innovation here is the low-intrusive part, because usually these kind of tools require, and AI models require, a lot of data of high granularity and of a large spectrum of features. So what we try to do is to make it much more practical in its application, using a very, very low set of features coming from the PV inverter and from the heat pump, instead of utilizing too many features in that sense, since practically these are not usually available in everyday applications. The fifth tool for CERT is a black box MPC, a black box model predictive control for the fan coil units used as emitters, as emission systems of the multi-source heat pump. So it's a fully data-driven MPC service that controls emission units per zone individually in each room to reduce the thermal energy consumption without jeopardizing personalized indoor thermal comfort. What I have to say here is, and to underline here, is that aside from the energy consumption that we try to of course, optimize, we don't just forecast situation or conditions. We control, we actuate, we generate control decisions that are directly applicable to the fan coil units. And another thing that I would like to underline here is that we consider a personalized and individual, let's say, profiling per room for the different tenants and users of the building. So the optimization here is tailored to each, let's say, tenant's needs, instead of let's say, considering a generalized, let's say, approach based on any international standards. The sixth tool that CERT is delivering here and is developing here is electricity flexibility management at building and district scale. So it's demand response, actually, in practice service that collectively addresses grid signals and unexpected congestion incidents in a proactive manner. Also, of course, based on real flexibility estimations and not as usually is done in other practices or in literature, the untapped flexibility. So we don't consider the maximums or the minimum operational bounds of the systems, but we try to estimate the real flexibility according to users' needs and users' habits. So we don't want to intervene with them, and we try to stay within their preferences and habits always. This is the baseline for this approach. So we capitalize on that. Of course, we capitalize on, let's say, grid signals, congestion for expected congestion, and of course, the available renewable energy generation or renewable energy availability from batteries in order to also optimize the entire system as a whole, reducing energy costs and grid dependencies, of course, without jeopardizing, in this case, flexibility bounds extracted from past habits of the tenants. That's it. That's all from my side. Hopefully I was not very quick. You could.
No, we have
Okay.
time. Well, we are in advance. Bernard, the floor is yours.
Thank you. So let me share the screen. Okay, hopefully you can see the slides.
Yes.
Oops, sorry. Okay, so hello to everyone. My name is Bernard Jenko. I'm a computer science researcher. I mostly do research in machine learning, AI, and decision support, but I also have some background in electrical engineering. And what I would like to talk about today is an aggregator platform for explicit flexibility. So this is a system that we are developing within the SEEDS pilot. So this is pilot which is located in Slovenia. And in this pilot, besides my institution, which is Jožef Stefan Institute, we have two companies collaborating. So one is Petrol, which is energy provider. They own a large number of gas stations throughout Slovenia and the Balkans. And the second company is Elektrocelje, who are a DSO, so they are a distributor of electricity, and they are in charge of stabilizing local electricity grids. And the idea of this pilot is to investigate and to develop a system which would be able to extract or use flexibility that would be available within individual buildings, like in our case, this will be gas stations, and to use this flexibility in order to stabilize the grid on the local level. So before we start describing what we have developed, perhaps a few words on electricity flexibility services. So what exactly this is? So in essence, we can distinguish two periods of electricity grid, right? So in a traditional grid, basically the grid was stabilized or balanced on the side of power plants, right? So basically power plants adjusted electricity generation in order to meet the demand, right? Because we know that supply and demand in electricity grid needs to be balanced at all times. But in a more modern grid, right, that we have, let's say now, which became more prevalent with frequent use of solar power plants, wind power plants, which are not really producing electricity continuously, right? So in this modern grid, we need to use some so-called flexibility services to manage and consumption and also generation of electricity. And these flexibility services are actually services which would somehow adjust and generation of electricity and consumption at all times, right? So our pilot basically is trying to develop such flexibility services on the level of individual buildings. So we try to investigate how to exploit these assets that we already have at buildings in order to provide flexibility and, of course, to stabilize the grid. So within our pilot, we had some objectives that we wanted to address. And basically, we wanted to develop a set of components for enabling this flexibility of ours, right? And these components could be used in already existing buildings. So as I mentioned, our partner Petrol is owning a large number of gas stations, and these gas stations were actually our target. So we tried to equip these gas stations with some controlling devices that would enable to extract flexibility out of gas stations. And of course, all these devices that are already installed at gas stations have to be connected to an aggregation platform, which then in the end controls the devices and provides the flexibility. So our main objective was to exploit this energy flexibility from the existing buildings. And of course, we want to do this in connection to our distributor, which actually sends us a request for flexibility. And because of this, our scenario is on-demand or explicit flexibility. And of course, our system in our pilot is evaluated in a set of gas stations owned by Petrol, which are located in different parts of Slovenia. So if I try to explain our use case for explicit flexibility in more details, so here we have this chart of actors in this diagram, but in essence, this chart basically tells us that once we get a request from our distributor, Elektrocelje, right? So they actually have their own predictive models, which assess how much their grid part will be in need for, let's say, either additional electricity or they will have too much of electricity in a certain part of the grid. And given this information, they send a request for flexibility. So this can be either positive or negative flexibility, which basically means that they can request that we reduce electricity consumption or that we increase electricity consumption, right? And basically this request is sent to our partner Petrol, or basically to our aggregation platform. And this request is then automatically evaluated, which means that our aggregation platform somehow estimates whether this request can be fulfilled for the next day, and if it can be fulfilled, what will be the let's say the benefits for the prosumer, which is petrol company, right? So basically, this means whether they will have some decrease of electricity costs or not, and what will be the risk of basically providing this request. And of course, in this scenario, also a decision maker, a human decision maker needs to be involved. And basically, in the end, the human decision maker decides whether to go for this request or not. And when the positive decision is made, then the system basically automatically controls the devices in a way that the requested flexibility will be provided. And the same story can be also seen in this plot, right? Where on the x-axis we have time. So this basically means that on the left-hand side we have this part when we get a request. We estimate whether the request can be fulfilled or not. And then the part of the plot on the right-hand side basically shows the electricity consumption when the flexibility is needed. And this bolded part of the graph is actually the change of the normal electricity consumption, right? As we can see, we have used a bit more of electricity before the flexibility was requested, which is this purple bar, right? And then within this purple bar, we have lowered our electricity consumption, right? So this is how the flexibility should be delivered, right? But now, how do we actually manage to assess and provide this flexibility? So on this slide, we can see the concept or architecture of the aggregation platform. And of course, the main part of this aggregation platform are predictive or forecasting models, which basically tells us how much electricity do we estimate that we will actually use within the next day. So this is this blue part, right? And these models are, of course, trained based on data that are collected in previous month and so on, and they are built with machine learning. So they are completely data driven. Now, having these models, we have this green part, which is flexibility estimation. So this part consists of models that actually tells us that basically they tell us how much can we reduce or increase electricity consumption without actually violating some boundaries or user preferences and so on, right? These are actually models that establish some flexibility bounds of our system. And given this input, we then have another part, so this red part, optimization part, which actually uses this input in order to find the best alternative schedules for using or controlling the devices, right? And of course, in the end, we have this decision support module where a decision maker basically makes the final decision whether a certain scenario will be selected or not. So this is, in principle, how the system works. Now, regarding the details or how this system is basically installed on a location, so, for example, for one of the petrol gas stations, which is located at the Bled, we have included in our system a set of devices that are listed here. So we use the heating, ventilation, and air conditioning system, which is based on a heat pump, right? We include a heat pump which is used for heating water for car wash. We use a heat pump which is used for domestic water heating. We use a solar power plant and so on, right? So all these devices are connected to our system. And in these images, we mostly, we can see how this system works even before we started our pilot, right? So these are some SCADA schemas which are used to control these devices, right? So these are the devices we have used. And then these devices are connected mostly via HTTP protocol, but also we use different protocols for connecting different devices. Because, for example, certain sensors in the buildings, such as door sensors, use some cloud-based interfaces and so on. So here we had quite a few issues to connect all the systems that are produced by different vendors and connect them to our system, right? But nevertheless, on the left-hand side, we have the system which is installed at the location, and then data is pipelined to a central server which is located at our institute, and then connected to the distributor, so that we have established all these connections for the system to work properly. And here we have another example of how the human decision maker will, so what kind of information will human decision maker get in order to select the most suitable alternative, right? So on the left side at top, we have some, let's say here we can see basically 3 different alternative solutions which differ in cost. So this is the x-axis, and the risk is on the y-axis. So basically a human decision maker can select between, let's say, higher monetary benefit and lower or higher risk, right? And then on top, on the right-hand side, we can see the time plot of how the cost is changing through the period when the flexibility is being delivered. And then on the bottom, we have a different estimate of costs, risks, energy consumption, bonus that was earned by providing flexibility, and so on. And finally, at the lower right-hand side, we can see the profile or schedule, how the individual devices were controlled during this flexibility delivery. So to summarize, within this pilot of the SEEDS project, we try to provide some flexibility services which are a crucial part to modern electrical grids. And we try to use the existing subsystems for heating and cooling in the distributed buildings to provide this flexibility, right? And as a consequence, if, for example, a building would provide some flexibility, right, it would also reduce the costs for electricity. And of course, we have now 2 benefits. So one is reduction of costs, and another benefit is also stabilization of the electrical grid, right? And of course, if our system is connected to the DSO automatically, right, it can more or less function autonomously, right? So these are somehow the benefits of the system that we developed. And that's more or less all I had to say. So thank you.
Thank you, Bernard. So thank you, Bernard, and a huge thank you to all of our speakers for these insightful presentations. It's fascinating to see how all these pieces fit together in the real world. Do we have any questions? I don't see anything on the chat, but it's time. If you have any question, you can write. Okay. We can, I think, wrap up the discussion here. Okay. If there is one main takeaway from today's session, it is that truly decarbonizing our buildings means going beyond the boiler. As we have seen with the SEEDS project, it's about moving away from isolated interventions and adopting integrated performance-based upgrades that combine smart technologies, renewable and demand-side flexibility. We hope these insights will be useful for the municipalities, facility managers, and policy actors joining us today. I want to extend a massive thank you to our four speakers, Vula, Apostolos, Iakovos, and Bernard, for your time and expertise today. And thank you also to the EU Sustainable Energy Days for providing this great platform. And also, please don't hesitate to visit the SEEDS project website and follow us on LinkedIn, on X, follow our newsletter to keep up with the final results of our pilot site. And don't hesitate to reach out to our speakers or to SEEDS if you have any questions. And thank you for attending and have a wonderful day.
Thank you.
Thank you, Anaïs. Thank you all.
Thank you.
Thank you, Anaïs. Thank you, everyone, for being here today. Bye-bye.
Bye.